Hello. Uh, these are some workshop exercises of GeoTool Pro book. Might be helpful for those mechanical engineers who willing to learn GD&T. This book you could buy from GeoTool website and also available at Amazon. So this first exercise is all about introductions to GD&T and the symbols that we use in mechanical engineering drawings. The first one is name of current American national standards on dimensions and tolerance. It's ASME Y14.5 2018. And here on mathematical definitions of dimensioning and tolerancing, we refer this one ASME Y14.5 and we revise it in 2004. The ISO standards, we call it in ISO 1101, the GD&T with a very different name. We call it Geometrical Product Specification (GPS) in ISO 1101, while in the SME 14.5 we call it GD&T. Here in this exercise we have to label the following symbols. The feature control frame, all of these are my feature control frame, this one, and then this one, and this one also. These are my feature control frames. Then basic dimensions, these dimensions in a rectangular box. All these dimensions are my basic dimensions. This 15 in rectangular box, this 80 in rectangular box. The two place designation for this here it's a two place designation to X in the front of dia 8. This symbol is for two place designation. Then square symbol. Here is the square symbol in this rectangular box in front of 6. All around symbol. Here you could see these two lines. At the intersection of these two lines, we have a small circle. So it's a all around symbol. For countersink, we use this symbol, this one. And for counterbow, there is a counterbow symbol in front of dia 10, like this. It's a counterbow symbol. And datum feature symbol. Well, all these are my datum feature symbols. This B and this C and this A also. These are my datum feature symbol. Then a reference symbol, it's here. You could see this dimensions in bracket 60. So these dimensions in brackets are for reference, and this type of symbol to show the dimensions for reference, we use this brackets and we call it a references symbol. For depth, here is the depth symbol in front of 5, like this in front of 5. For diameter, here it's in front of 8, in front of 9, in front of 5, zero point 0.5. These are the diameter symbol. Then here we have to identify the types of tolerance. Okay, so the first is flatness. This is the flatness. It's straightness. This one is cylindricity. Then circularity, perpendicularity, parallelism, then angularity, position, profile of a surface. It's here, this one, and profile of a line, then total runout, uh, for circular runout, uses like this symbol, then concentricity is like this, and symmetricity we have this one. Then what type of tolerance these are? The first one is these four are the foam type of tolerance. This form type of tolerance, and these three are the orientation, angularity, perpendicularity, and the parallelism are orientations. For location, we give these type of tolerance, the position, profile of a surface, and profile of a line, and these two total runout and circular runout are the location runout, and the concentricity and symmetricity are the location of derived median points. Here, this one, the location of derived median points, concentricity and symmetricity. Here again, we have to identify the symbols. So the first is of free state, and this one we use is for free state, F in a circle. Then second is spherical radius. Here, this one we use is for spherical radius, SR. Then projected tolerance zone is here, P in a circle. Then tangent plane, and here is the tangent plane, this one. We don't have any symbol in ISO standards 11, ISO 1101 standards, but in ASME 14.5, we have this T in a circle for tangent plane. And for list material condition, we use this L. And unequally disposed tolerance, we use this U. And for translation, we use this uh, equilateral triangle. I give it a 7 number. And spherical diameter, let's give some numbers here. Spherical diameter 8, it's 11, controlled radius, and maximum material condition MMC, it's 13. So spherical diameter is here, the first one, number 8, and dimensions horizon. Yep, we use this one, 9 number, and all our dimensions, So we have seen in previous exercise also. Uh, this one is here. It's for overall CF. Then we have this controlled radius. It's here, CR. CF is for continuous feature. The CF for continuous feature, and MV uses for maximum material condition. I give it a number 13. And here, uh, label the feature control frame. Okay, the parts of this feature control frame. This it's a feature control frame, and the first one is our. Okay, we will start from here. Uh, Shape of the tolerance zone. Here, this diametric tolerance, this diameter symbol is the shape of our tolerance zone. So one and datum feature modifier. So it's here with B. We call it a datum feature modifier, and here it refers to the maximum material boundary. It would be 2. Then tertiary datum feature here. C is our tertiary datum feature, secondary and primary. Then next is feature tolerance. Here, this point 0.5 is our feature tolerance. So I can give it a number 4. Then 5 is primary datum feature. It's here A. Then geometric characteristic symbol. Well, it's here. Position is our geometric characteristics, and the secondary datum feature is V7, and feature modifier is here. Maximum material condition with this zero point 0.5 positioning tolerance. It's 8 number. Then yeah, in next exercise, we have to identify the maximum material condition and least material conditions of these features here. So here the least material condition LMC would be 0.75, and the MMC, uh, it's for hole, and for hole we this 0.75 would be its maximum material condition MMC, and uh, LMC would be 0.755. Again for this here, this would be MMC zero point 0.5, and this one is LMC. And here 4.006 would be MMC, and 3.994 LMC. Here this is MMC, this one, and it's LMC, this one. Again, this one is MMC here, and LMC, this one. Here in next exercise, uh, the size tolerance controls the size and the form of a feature. The correct option is C. And what is the maximum ball allowed on this pin below? Well, yeah, this minus this, we get a point double o 3. So answer is A. The maximum ball allowed in this pin is A, point double o 3. And if the pin is produced at a size of point 499, the maximum form of variation, it's 0. Answer is A. And here we have to identify the actual matting envelope and actual local size. So the actual matting envelope is a plane that touches the highest point of a machined part or non-machined part. So here this side, this one is actual matting envelope, and this side is actual local size, and the plane touches the highest point is the actual matting envelope. Then here, uh, when we use a pin to verify size of a hole, yeah, it measures a matting envelope. It means a matting envelope on the shaft below with only the size defined. So we when we don't have any datum feature here First of all, we have to define a datum feature. We actually cannot define this coaxiality tolerance here. Uh, we don't have any datum feature here, and so it's not defined here. On the pin below, with only the limits of size defined, perpendicularity tolerance. Well, perpendicularity tolerance here would be the sum of this plus minus tolerance. So it would be 0.006 is the perpendicularity tolerance. Then here, circle the size dimensions. So this is my size dimensions, and this diameter is my size dimension. And why I circle these dimensions as my size dimensions, because of the size dimensions are those dimensions that we could measure directly with the instruments like vernier caliper, micrometers, and bore gauge. We can measure directly, and these dimensions we cannot measure directly, these ones and these ones. So these are the size dimensions, and here what is the maximum and the minimum clearance between the pin and hole. Maximum clearance, it would be uh, maximum size of hole and smaller size of pin. Point 377 minus point 373, so it would be point double o 4. And the minimum clearance, it would be minimum size of hole 0.375 minus this maximum size of pin 0.374. It would be a point double o 1 thousandths of an inch. Um, then name and application for running and sliding feeds. We have translating shaft, bearings, and then bushings. So these bearings and bushing are the running and sliding feeds. And what type of feeds would be the best for application with pivot hole and shaft that must be freely assembled and disassembled? Locational clearance feed we can use here. Locational clearance feed. Uh, well, force feed will provide some more interference, and tighter feed LC3. Oops. Okay, LC3. Uh, and to solve these problems, uh, to find out the size and the maximum clearance, we uses these tables. These tables is in inches. I took it from the same GeoTool Pro book, or you could search online for metric system also. So, like here, in 7 number for RC4, RC class 4 running and sliding feeds, uh, for the range of 0.12224, we have this data. We have hole at 6 and shaft G5. Here we get the clearance and the size is here. And similarly, we could solve this one for RC2, for RC4 at number 7. Here is RC4, and this is the answer. Then here, MMC of 68 diabos. Here it's 68.2. So the answer is 68.2, and the position tolerance is at RFS regardless of feature size. We don't have any feature modifier here, so it's a regardless of feature size, and that's why the MMC of this boss is 68.2. How much position tolerance is allowed if the size is produced at 68.1? The position tolerance would be same. It's a regardless of feature size, so it would be zero point 0.3. And the MMC of three holes, well, here is the three holes, and for holes, we would subtract this one and this one, so it would be here 14.8 and 0.35, and it gives us 14.45. 14.45 is the MMC of those three holes, and the position tolerance if three holes are at 14.8, here the position tolerance would be 0.35. Then next here is how much position tolerance is allowed if three holes are produced at a size of 15. Okay, so it would be 0.55, and the perpendicularity tolerance for two datum A, uh, it would be this point for three holes, and for this center hole it would be zero point 0.2, and does the 94 ball circle dimensions have tolerance? Well, it's a basic dimensions. We know it's a basic dimension, so we don't have any tolerance here. So here we have to define the datum feature symbols, and if I say this one is my uh, this surface is my datum feature one, primary datum feature, I can define it here. My datum feature A, and I can define my datum feature B over here, which is this side. This one here, this side is my datum feature B. I can define here like this, and my datum feature C I can define here then we can say these are our basic dimensions. This one is basic, this one is basic dimension. Okay, then here uh, we have to draw the datum feature symbol and the flatness. on this right hand side face, and for this flatness, for this is a flatness symbol, and the point 005, this is the requirement, and I can say this is on this face, and this is my datum feature symbol. This is my datum feature A, primary datum feature. Then next, top surface of the front view as datum feature B. So, and the perpendicularity with datum feature A. So this is the perpendicularity sign of point 005 with the A, datum feature A. Then this is my datum feature reference frame, and I can call it my datum feature B. Then third is left surface as a datum feature C, and perpendicular to datum feature A and B. For this, this is my perpendicularity of point 005 with A and B, and that would be my okay. I'm just making here, that would be my datum C, and this is my datum difference frame DRF with this surface, and this is my datum feature C. Then all the necessary dimensions as basic. Well, we can keep this one basic. This one is basic. Then position 0.250 hole with a diameter of 0.55. Uh, oops. So this one 0.25. Here is this 0.25 of position this hole with a diameter of okay. So this is my position symbol, and 0.005 is the positioning tolerance, and it's regardless of feature size. So with datum feature A, B, and C, and this would be my datum feature reference frame for this 0.25 O hole. Then next is position the three holes with a diameter of okay, these three holes. So this is my position symbol, and the tolerance is diametric tolerance. So this is diametric symbols, and this should become here point 012 at mmc. So we will write this maximum material modifier symbol related to datum A, B, and C. So A, B, and C, and this is my DRF for these three holes. Then identify the upper right corner Y. Okay, here is Y, and then lower left corner as X. So I identified it as X and apply profile tolerance of point. So profile tolerance would be like this point uh, 02 with the A, B, and C. And I have to write down here this from X to Y, and this and here on the produced part drawing below, we have to tell the tolerance zone that we have applied in previous problem. So this one be my profile tolerance zone. This one point 0.02. Our profile must be lie between this zone of point 2. Then our flatness that with datum feature A, this flatness here in between these two lines, uh, this one and this one in between these two lines, the flatness and the perpendicularity over here. Uh, the one perpendicularity you can show here, this one here, the top face C with datum feature C, and one perpendicularity is here, and the positioning tolerance for the three holes, it's in the center of the holes. Then next here we have to tell the diameter position tolerance with produced size, with different produced size. It's at 2.248. It would be 0.01, and this size 0.249. It would be point double one, and here it would be point zero 1 2 and point 0.013, and then so on, and here it would be point 0.016. So at the time when we produce the part at this size, the position tolerance would be here point 0.016. Then here it would be with this regardless of feature of size. We don't have this feature modifier, then it implies to regardless of feature size. Then here we have some drawings of the parts, and here we have the produced part dimensions, and we have to verify if the part is accepted or part is rejected. And normally we use these Excel calculators to find out this if the part is accepted or rejected. Like here, we will fill the values here. So for here, for first of all, MMC would be 15.1. Okay, and the actual size for first hole is 16.1. So it's 16.1, and the x deviation is our, if I say this one is my x direction and this one is y direction. So x is zero point 0.1, uh, it's 30, and now we got this 29.6, so point 4. So x deviation would be point 0.4 here. Uh, this and then the y deviation is here. It's 25, and we got to 25.3. So here I will write zero point 0.3, and actual position is 1, which is less than the 1.6. So we get here this green uh, formatted cell, and this green formatted cell means the part is in accepted. Then again, here we could solve these problems with the same Excel calculator. Uh, uh, the MMC size here for this holes 9 minus zero point 0.2 would be 8.8. Here it's 0.8, and the position tolerance is zero point 0.8. Regardless of feature size, the actual size we got here of 9. Let's say for hole number 2, the actual size is 9, and allowed position, then x deviation. So this one would be my x deviation, and this one is my y. So x deviation is zero point 0.1, 28 is the actual uh, dimension from here to here. Then zero point 0.3 is in y direction, and the part is accepted. Then here in this exercise, we have to calculate the virtual size of this hole and this pin at MMC. So for this hole, the virtual size would be 0.180, and the positioning tolerance with MMC, we would subtract this one. So it would be 0, 1, 2, and it will give us 0.168, and the virtual size uh, with this datum feature A, the perpendicularity tolerance is here, and here the virtual size would be this 0.180 minus this 5000. Uh, it will give a size of 0.175. Then next here for this pin, MMC would be 0.377 plus this position tolerance, which is 0.010, and we will add this. So point, oops, 0.387. The virtual size is 0.387 here, Then for here, this perpendicularity tolerance. With this perpendicularity tolerance, the virtual size would be 375, 77. Then in this exercise, we have conditions that our ring must lay flat on the face of mating parts. So if we follow this condition, then we will add the perpendicularity of this pin at the maximum material condition, and that would be the diameter of this ring, and then ring could lay flat on the face, and that would be my MMC of the pin, which is 0.377, and my positioning tolerance is this excuse me, this one, perpendicularity tolerance. It's a point double O 02, and it gives a size of 0.379. So the ring size in first case is 0.379. Then here the condition is of ring must lay flat on the face and line up to with these two edges, this first one and this one, the second edges. And for this we will add the positioning tolerance of the pin. So MMC of the pin with position tolerance is here. We already have calculated. It's 0.387. So in second case, the answer is 0.387. And here, ring does not have to lay flat on the face, but must fit over the pin. So we don't need this perpendicularity tolerance. We don't need this positioning tolerance. Only we do care about this 0.375, and the size of the pin at MMC, it would be 0.377. Then here, okay, use the upper virtual size and calculate the position and perpendicularity tolerance. So the perpendicularity tolerance for this pin, uh, first is the sign of perpendicularity, the symbol of perpendicularity. This would be MMC of the ring. It's 0.382 here. MMC of the pin is 0.382. Then we will subtract the MMC of the uh, pin, and here MMC of the pin is here in this case. When we added this perpendicularity tolerance to find out the MMC of the pin, and here we have the same condition, the perpendicularity tolerance we are finding out for the ring, and we are added the perpendicularity tolerance here, and we got the 0.379. We will subtract this 0.379 from here. So my perpendicularity tolerance would be uh, 0.003, and with the maximum material condition, I'm writing this out because of the space. And Here in this ring 2, we have to find out the position. So the first is symbol of the position, and the MMC for this ring is 0.393, and the MMC of the pin with its positioning tolerance, it's here 0.387, and we will subtract 0.387. uh, and we get point 006. So this is the position tolerance here. And then here in this exercise, we have to label these points, lines, and planes. So everyone know it's my point. These are my axes, these are my lines, and this is plane. If I say we have to show these 3 degree of freedoms for translation and 3 for rotations, it's Y, and this axis is Z. Then my Z axis can translate in this direction like this. Y axis can translate like this, and X axis in this way. Then here we have to label these terms. So the K is datum feature symbol. The first one, it's K. Then the surface of the part, it's a datum feature. Surface of the plate, it's a datum feature simulator. And the plane derived from the surface plate is a simulated datum. And theoretically perfect plane is datum.